Today we're talking about parameterized surfaces and some results. Before we get started, let's talk about parameterized curves because it's a little bit easier. It's in 2 dimensions, and we can take a look at some results, some aspects of parameterized curves that can be seen as analogs to parameterized surfaces. So if we start with a simple curve, I'll start with a circle. It's not that simple, but I'll start with a circle. So the way we do a parameterization for a curve is that we have one variable, t, that does something to an x function and a y function, and based on that it'll draw something out. It'll give us values for x, values for y, as one parameter t changes. So if we have x going from x is just equal to t, and y of t equal to the square root of 1 minus t squared, and then we'll let t go from -1 to 1, then we have a graph of something. And we can actually take a look at this graph using some sort of graphing program. And then take a look at what the image of this is going to be. So as we might have guessed, could you have guessed this? That this was going to be a circle, or at least the top half of a circle, being drawn from -1 to 1. So it turns out that we found a more efficient way to draw a circle eventually, right? And I think the more efficient way for us to draw a circle would be if we let our x of t equal to cosine t, and our y of t equal to sine t, and then this time we let our t go from 0 to pi, and then we might have a better chance of drawing the circle, or another chance of drawing a circle, but in some cases a little bit more efficiently. So let's try that in our graphing program. Equals cosine t, sine t, and I have to draw my graph from 0. I have to change the limits from 0 to pi. So it draws basically the same thing. Now, aside from the drawing itself, the image that it has, or aside from the values that we're putting in here, what do you think are other differences between these two curves that are drawing? Or that are being drawn? Any ideas what the differences might be, or what the differences might be? Orientation is a big difference for us. For some problems, it turns out to be a bigger difference than others. So the orientation is a big difference. it turns out that when you're drawing this first example, going from 1 to 1, it draws, you're going in order from least to greater, and then it turns out that it draws this top half of the circle in a clockwise direction with a starting point at -1. -1, 0. On the other hand, this other graph over here starts at 1, 0, and it goes in the counterclockwise direction. And then that's, so although the images look the same, the way we're drawing this might be different. So there's some importance in these curves and how they're being drawn, not only importance in the types of functions that we'll be dealing with, like in this first example, where we'll have a square root to deal with, and that might not be so attractive when we're doing things like taking integrals and derivatives of these things. So the second one is a nicer example, but the orientation is also makes a difference. And if you're computing the work that it takes to go around this curve from one point to another, the starting and ending points do make a difference as well, in that, you know, this is going to give us a different answer for your work being done. So we can see, just as an example with the curves, that there's a few ways to do there could be a few, it could be an infinite number of ways to be able to graph the same image, and depending on how you graph this, the orientation might be different. And so we're going to be concerned about those couple of aspects of things. So now let's go into surfaces, and let's take as our first example for surfaces the surface, the paraboloid y is equal to, or sorry, z is equal to x squared plus y squared. And when we look at these surfaces now, we can think about a parameterization where we're parameterizing the surface. So when we parameterize a curve, we have one parameter t that takes us to a one-dimensional object. By the way, I gave examples of curves in 2 dimensions, but we can also have curves in 3 dimensions as well, right? The helix is our famous example for drawing a curve in 3 dimensions. So a curve is parameterized by one parameter. So now imagine having some x, y, and let's go to z, x, y, z functions that are being parameterized by not just one parameter, but by 2 parameters. Maybe this was not a good first example, the x squared plus y squared. Well, let's just keep it there anyways. So think about a surface. It makes sense now to go from a one-dimensional wire, a one-dimensional object like a curve, whether you're looking at it in 2 dimensions or 3 dimensions, parameterized by one variable or one parameter. Now, a surface must be parameterized by 2 variables or 2 parameters. And what we call this parameter, or these parameters, does not make a difference to the image. In most graphing programs that I've dealt with, they tend to like using u and v There's some that use S and T, but we can use whatever we want. So now let's introduce ourselves to being able to parameterize by two variables. And I think the two programs that I have in mind is using U's and V's. So let's take a look at a way to parameterize this paraboloid. And what we'll do is we'll set up, we're going to do this in 3 dimensions. We're going to set up a set of equations that would have 2 variables in it. And we'll call this one just U and then this one just V. And Z would just be, well, if X was equal to U and Y was equal to V, what do you think Z would equal? U squared plus V squared, since X squared plus Y squared is what we're looking for. And so if we take that and try to graph it, we should see a paraboloid. Now, just to try to encourage you to do some of this on your own, I'm going to not use this program anymore, although this program is really, really super easy for me, and use that calc program, 3D plotter. So I would encourage you to try to use this just to be able to view graphs that you might be working with. So just to show you a couple of options, I've unchecked this function. If I have this is the default that you'll see when you first start the program, is that when you have this function checked and then you see this is the first function that you see. But there's other options here that I'd like to let you know of. I'm not too concerned about graphing functions, although we've studied that already in chapter 14. So I'm going to uncheck that and clear everything out. A way to graph parameterized curves or surfaces would be to go under Graph and add a parametric surface, it says here. So I'll click on adding a parametric surface. And here I have a sample surface that they've given me. And it looks like it's cosine of U squared times sine of V, or cosine of U sine of V. Anyways, I don't want to graph that one. I'm going to take that one out. And instead replace it with the parameterization that we came up with. And this doesn't have nice text formatting, so you have to use the caret for your powers, and you have to make sure you use parentheses whenever appropriate. I didn't talk about the limits for U and V, but whenever we do parameterized surfaces or curves for that matter, it's always important to know when to start and stop. And for this one, I'm going to change this, but for now I'm going to go from 0 to 2 for both the X and the Y, and then I'll have these to be the same number, and we'll take a closer look at what these things mean, the steps for U and steps for V, and how they would affect your graphs. So I'll hit graph, and I'll see that this thing really has nothing to do with below the z-axis or the xy plane. And so whenever you want to change your boundaries or your zooming in and zooming out, there's this format axis option where I can change my z minimum and z maximum so that I don't have any negative z values anymore. And that will just allow me to take a look at my graph a little bit better. This does not look like a paraboloid. What do you think I'm missing here? Help me out here. How can I make this look like a I know a paraboloid to be like a bowl thing, right? So based on the screen that you're looking at now, what seems to be missing in terms of making this paraboloid look like a hole? U only goes from 0 to 2. Yeah, so why don't we throw a negative, make it go from -2 to 2, and probably the same for V. Looks like U and V are essentially X and Y, right? So why don't we change the U's and the V's, and then now if I hit graph again, I'll see a fuller looking paraboloid. Now, the steps for U, let's think about that. Steps for U, I have 20. You could do something ridiculous like make it into a really small number. I don't think this will accept anything less than 2. So if I have 2 there, before I press enter, what do you think is going to happen? Do you think it'll shrink?
It won't be as rounded.
It won't be as rounded? Let's see what happens. What? Okay, so I see something kind of weird here. I kept the number of steps for V, so V was equal to Y. So it looks like I have my Y-axis, and the way graphing programs work from computers to your calculators is that they don't really graph the graph. They plot points, and then they connect the points with lines. So anything that you see in the graphing program are all connected with lines. So this is being honest with you in a sense that they're actually drawing the lines that you have. So what they're saying here is that along the V parameter, which happens to be in this case my Y, along the Y, I'm making 20 steps to draw my graph. Along the X, I've made 2 steps. I start from -2. I guess this is -2 down here. And I take 1 step, 2 steps. So those are my sample points, and based on my sample points, this is all I'm getting. So if I were to make this into 3 steps, or 4 steps, it's starting to look a little bit more like a paraboloid. If I take this to 5, 6, or 7, it starts to get smoother. And then if I match it up to 20 like it has here, then I see a little bit more like a paraboloid. So if I do 40, it's going to be even more refined, but at some point to your eye, it's not going to make much of a difference anymore. So this is just doing more calculations for the computer than what's needed. I can even go 100 steps to make it super smooth. Again, it'll show you the lines that it's making those sample points on, but it wasn't much different from the 20 that we had earlier. So the computer just does a little bit more work to find the more refined values. So what do I have here, though? If you look at it from the top, I think when I first drew a paraboloid in the other graphing program, I got a picture like this, and I see that they have these 4 spikes coming up. Any ideas what that might be? Can you explain what that is? The 4 spikes coming up? The what? The boundaries. They're like the boundaries for the U and the V. They were the boundaries for the X and the Y. If we look at this with a flatter perspective, you should see a square on the XY plane from -2 to 2 and -2 to 2. And these points on the corners get plotted into this z value, and then they go up higher than the rest of them. Okay, so let's see if we can recap what happened here and try to draw our paraboloid. We said that our x and y, or u and the v, go from -2 to 2. So provided that we know that u is the first variable and v is the next variable, if we just set this like this, it would make sense. But just to be clear, we can say u, v, the points are within this set. So we have this, and now the drawing for this will give us a paraboloid, but it will give us a paraboloid with these little corners sticking out. You see those little corners? Mm-hmm. This is kind of like my surface, you know, except it's upside down, yeah. So my surface is kind of like, can be described as some sort of paraboloid, or at least a piece of a paraboloid. Anyways, what we're looking at here is the domain, and these corner points are the ones that kind of get sent up to the high points. So if we look at our domain, and since we are using u's and v's here, I think I'm okay calling this xy axis as a u-v axis instead of x and y. Although it might look like an x, y, z space, right? But our domain here comes from somewhere else, or we can think about it coming from somewhere else, but since x is equal to u and y is equal to v, we can easily slip those in, and it'll look like that's how it's related. That would be the domain that goes in for x, or for u and the v.
So we just like that, right?
Yeah, well, I had 0 to 2 in my drawing program, and then we decided that that was only a quarter of a paraboloid that I wanted to see, so we extended it to go to -2. Yeah, but that's where it comes from. And so if your domain, whether you're looking at the xy plane or the uv plane, if your domain is some sort of rectangular region like this, or maybe something that can be easily described in Cartesian coordinates, then this is not a big deal. This is a good thing. But now imagine if you wanted to shift your focus a little bit, instead of looking at a square or rectangular space down below, if you imagine your region, what if we imagined our region to be a circular surface? We're talking about a paraboloid after all. And if you had a circular region on the xy plane, then you can almost be guaranteed that your paraboloid will have a nice cutoff. It'll look like an actual cup that's flat on top. That would be easier for us to deal with in some cases. So thinking about it that way, we kind of think about this surface now. If we're attempting to parameterize this, we can start our attempt to parameterize this using polar coordinates. Or wait, polar coordinates in 3 dimensions, what's that called? That's cylindrical coordinates, right? So why don't we think about approaching this in a cylindrical coordinate kind of way? Now, how do cylindrical coordinates go? R, dr, d theta, dz. So we have the 3 variables, r, theta, and z. And how do they relate here? So x is equal to what? X is equal to, well, it's like polar, right? So r cosine theta. I'm going to erase things here. I don't know if you're taking notes in pen or pencil. And z is equal to z. Oh, wait, z is equal to this. That's just r squared, isn't it? Now, if I go on to my my program, I can't use r and theta. So why don't we do this? Why don't we change my r into u and change my theta into the other parameter v. Does it matter which one is which? We'll take a look at that question. That's a good question. We'll take a look at that question when we graph this. And if I forget before we move on, remind me. All right, so now I'm going to go back to my program. I don't know if I want to keep this, but just to let you know, there is a way to keep this program. I'm going to remove it right now to get rid of it. But I still have this window open, so I think that means I've kept it. And I'm going to open up another program going to graph another program, another parameterized surface. And so I can see in my window it says parametric surface number 2. I'm going to graph the same thing, but I might want to keep the other one just for comparison's sake. So this guy is supposed to be u times cosine of v, and then the second guy is supposed to be u times sine of v, and then the last one is supposed to be u squared. Now, I can press enter now, but let's just take a look at the parameters real quick. The u goes from 0 to 2 pi. What is the u? What did I replace u with?
Radius.
R, the radius. So the radius is going to go up to 6. I don't know if I really want to go that far. So what radius did we use to try to draw the graph last time? Yeah, it was kind of 2-ish. So why don't we change this into 2? How about the v? Does it make sense to go from 0 to pi? So v was theta, right? And if we want to see the whole thing, we tend to go from 0 to pi. Now, let's, I'm going to change the steps momentarily to 20 and 20, and then we'll see how these things will change. So if I graph it, I don't know if you could tell the difference between this graph and the graph before, aside from those little corners sticking up. Do you remember how the rectangles were drawn on the surface of the previous graph? Yeah, well, let's see if I can graph it here at the same time. There it goes. They're kind of rectangular, right? Or some sort of, and they're up on the surface, so they look different. So I'm going to remove that again and take a look at this again. Yeah.
The rectangles themselves are neater, but the connections are more angled. The area
Connections are angled.
itself is not as smooth.
I think the key is to look at it from the top. What do you think of when you see this? What? Spider web. A golden eye. It's polar coordinates. Remember how we drew the polar coordinate graph? All right, here, let me remove this one and graph this one again from the top. We see that the way we drew the first graph, we drew it using kind of more or less a rectangular region where our x and y are essentially replaced by the parameters u and v. And so the domain that we're looking at is described with a rectangular coordinate system. And now if we take a look at, let's remove this one and put this one back, we see that it's like a polar coordinate graph where instead of looking at the Cartesian coordinates, the rectangular way to draw things, where your graph paper looks like squares, this time your graph paper looks like spider webs. It has a radial distance going outward, and it has angles that we're looking at as we go around. So not only that, we get our prize of getting a polar coordinate paraboloid that is flat on top instead of having those spikes going out on the corners. All right, now let's take a look at the steps for u. U, remember, was the r value. If I take this into small steps, r, what do you think is going to happen? Let me ask this question. Is it going to have less lines going vertical or less lines going horizontal? So if we look at it from the top, r gives a radial distance, so r would be describing circles. So if I don't know if you can count, but there's 20 circles in there somewhere. If we cut this down to like 3, you should see 3, maybe 4 circles. Okay. So if we look at it from the side now, since they're sampling only 3 or 4 of these things, it's going to connect them with lines, and this is the best you can do. And we can get even smaller, and this doesn't quite look like a smooth paraboloid going outward. What? I don't know. I've never tried one before. Yeah, sure enough. I don't think it's going to give me an error. Yeah, it's pushing it. So the more steps you take, the smoother this is going to look like. Right? Now, our pi was equal to, or our v was the theta, and we're taking 20 steps to get to 2 pi all the way around. So what do you think would happen if we took less steps? Let's say I put 3 in here. What do you think is going to look like? Yeah, it's like a pyramid, although I'm taking 3 steps. 1, 2, 3. It might be a square-looking pyramid. Let's see. So if you follow the sides, it looks like it's still kind of smooth, but the way it's being drawn out, yeah, it's only 3 sides. It just, let's see if we put 2 or 1. I think 2 would give us a line. Yeah, it's just like a flat parabola. That's nothing. And I don't think 1 will work. Nothing. So errors are actually good because you know what you're doing wrong. So steps of 5, you get this like pentagon shape, but that just means it's trying to go around in 2 pi in 5 steps, and it's sampling those to draw. So if we the more steps we have, the smoother it's going to be. But again, in computer science, there's a give and take there. The more steps you have, the more your machine's going to have to do the calculations, and then depending on the types of calculations it's doing, it could take a long time. But it turns out that our machines are so fast right now, I could put like 200 steps here for both of these. And it'll draw what it needs to draw. It was a little slower there. I don't know if you noticed when I press enter. It had a lot of calculations to do. Then if you do it that way, you can't really. All you see are lines that draw the actual surface. So there's a give and take when you're doing stuff with computers. Okay. But it's neat to see your limits that you're creating and how they're being broken up. All right. So, by the way, the names of these parameters are just restricted by the program that you're using. If I don't really care about the program, and I just want to do this by hand analytically, I can call my parameter whatever I want. Like, there's nothing really to stop me here to call it theta for my first example, except I've been used to just calling it t, that it just seems natural to call it t. But since it's an angle that goes around in the xy plane, it seems like it would be more natural to call it theta. So for this first example in my surface, instead of calling it u's and v's, why don't I just stick with x and y, right? It just seems more natural, and that would make my z equal to exactly what my original equation was saying. And so that just means, likewise, I can use the r and theta that we've talked about. Which is the first example of where I erased all the variables and changed them. Now I'm putting it back. Because if I'm just doing this and getting my values, then it's really, I can just call it whatever I want. Okay? Oh, limits, by the way. This thing had limits also. So my u-v limits, if I let my u be the r values, this is going to go from 0 to 2, and my v limits go from 0 to 2 pi. And anything that comes short of 2 pi will give me only a piece of the paraboloid. Anything that goes more than 2 pi will start repeating itself and make it nonsensical or non-useful. What was your question? If we what? Oh, yeah. Yeah. So let's go back to that example. And what do you think would happen if we change this change the u's and the v's? Yeah. So the answer is nothing, but we have to keep an eye on the limits that we've set for u and v and make sure you change it the way you're supposed to change it. So if I kept it the same, my u only went from 0 to 2, and my v went from 0 to 2 pi. So it's taller, and then my radial angle, not radial angle, but my angle only went from 0 to 2, which is less than 6.28 or whatever 2 pi is equal to. So if I change this to 6.2, and then I change this to 1 or something like that, then I would have the paraboloid almost, right? And 6.2 isn't quite 2 pi, but that's why there's a little gap here. Okay? So the variables, the parameters are just names. You can call them whatever you want. So call them r, theta if you want. Call them x and y if you want, or call them u, v, or s and t, or whatever they have as examples in the book or in your homework set. It's all going to be the same. So that kind of addresses a little bit of the relationship that we're talking about here. Now let's talk about orientation. I guess before we talk about orientation, we still need to talk about a few more things. The other really good example when dealing with parameterized surfaces is your sphere. Sphere is another big popular one to be able to parameterize. Oh, one more thing before we leave this page is that sometimes I call this a certain name. I don't know if the book calls it a certain name, but this is a special type of parameterization where you're leaving it as an x and a y, and then you're leaving the z as a z. This is, sometimes I call this a graph parameterization. And this example, when we change it into polar, I sometimes call it polar, although really it should be called cylindrical parameterization. So we'll put both polar or cylindrical. And the reason why they're being called these is because we're using a specific change of variables to be able to parameterize this. So if we do an example with spheres, then we should be able to come up with another parameterization, right? A spherical parameterization. So let's do another example with spheres, and then we'll talk about orientation. So with spheres, we actually have two hemispheres if we're trying to look at the graph parameterization. So let's say x squared plus y squared plus z squared is equal to, and let's pick an actual value like 2 squared or 4 or 7 squared. So sphere radius 7, and let's parameterize it first using the graph parameterization way. And in most cases, this is probably not the best way to parameterize a sphere if we want to see the whole sphere, because this will take us to 2 halves of the sphere, because the graph as a function doesn't pass the vertical line test if you have the top and the bottom part of the sphere. So we have to do this in 2 pieces. The top half would be your x and your y and your z parameterization. Your x is going to be x, your y is going to be y, and your z is going to be the square root of the radius minus x squared minus y squared. So, and furthermore, when you try to graph this using a graph parameterization like this, you're going to have to let your x and your y equal to specific values. And if you do that, then you're going to have to change your x and y are going to have to be like functions or something like that, which is not going to be very attractive. And then the bottom half will be the same thing, except you'll have a minus sign. And so not only this, there's more issues coming up here, and the issue is that your x and your y have to be bounded with a circle on the xy plane. And so you're going to need to call on limits that are not constants, which may happen. But in terms of trying to graph this, a lot of graphing programs only allow you to graph things with constant limits. -7 to 7. So the limits for this make it kind of difficult for us. And the idea behind these things is we're going to eventually put these things in integrals. So the limits will become kind of important for us. Let's see if we can see what happens to this sphere. U, V, and then here we have the square root. How do you do the square root? SQRT maybe of 49. Let's not go to 49 here. Let's just, for graphing sake, let's just have a radius of 2 minus x squared minus y squared. How? Using these. So you see that issue with a graph parameterization, it wants a square domain, and because our graph is circular of nature, you get this little flat thing over here that they're trying to graph, and they didn't know what to put for that, so they just put 0. So z is equal to 0 for all those other points that didn't make sense. So that's what happens to that. And so we go to polar and see if we can do any better with this. And with polar, in terms of trying to draw this whole thing, we still have a little bit of an issue, because with polar cylindrical coordinates, you have your z is equal to the z, and you still need to isolate the z, which means you have a plus and minus. So you still have a top and bottom problem. But at least your domain now is going to be circular. And I'm going to stick with r's and thetas. So you got the usual r sine theta, r cosine theta, and then your z is going to be the square root of 49 minus x squared minus y squared, which will amount to minus r squared. And then you'll have a bottom also. But at least your domain now is going to be a little easier to deal with. R goes from 0 to 7, and theta goes from 0 to 2 pi. So let's see how this thing's going to look like with our graphing program. So u times cosine v, u times sine v, square root of u. So the u, which is the r, goes from 0 to 7. I'm just going to go to 2 for this example. And then the radial stuff goes from 0 to 2 pi. So it's a nicer looking sphere. But then we still have the issue about the bottom part. So we can have another parameterization to get a bottom part. So, okay. But remember that we have one more coordinate system that really caters to spheres. And so if we go with a spherical coordinate parameterization, instead of the polar coordinate parameterization or cylindrical, or instead of the regular graph or function parameterization, we could do this using a sphere. If you remember when those guys were presenting this, they gave formulas for these things, right? What was the x equal to? The D stuff doesn't come in until we start dealing with integrals. So we'll deal with integrals in a minute, but cosine theta. Are you guys taking notes in pencil? Yeah. Phi. So remember that if you remember that r is equal to sine phi, then that's kind of like your thing. So remember when we first started talking about surfaces, parameterizing surfaces, that when we parameterize surfaces, we have two parameters. I have three variables here, rho, phi, and theta. One of them has to go. Let's put it this way. One of them is actually constant in talking about a sphere. Remember, spherical coordinate describes a solid with rho, phi, and theta. We're actually describing a solid. Think about those fruits that we had. They were solid fruits, except for the cantaloupe, but we compensated for the hole that's inside of the cantaloupe, that empty space in there, right? So as solids, we would look at parameterizing the solid with three variables. But we're parameterizing surfaces, and all we want is the outside surface of the sphere of radius 7. So what in these three variables, rho, phi, or theta, which one is going to be constant? Rho, phi, or theta? Rho. Rho is constant. Okay, because rho is the radius. If we're looking at the sphere, we're looking at this infinitely thin outside covering of our watermelon, just the outside. And there, your rho doesn't change. Your rho is just fixed at 7. So with a fixed rho, now I only have two variables, phi and theta. So I can let one of them be u and the other one be v in my program, and then draw it out, and I should see a whole, if I do my limits correctly. I should see a whole sphere come up. So let's take a look at that. Just for convenience sake, I'm going to let my u be phi and my v be theta. And my 7 equal to 2. Which means my u limits are going to go from where to where? 0 to pi, and my v limits go from 0 to 2 pi. And I think steps of 20 is good enough. I probably want to double one of them just to make it look nicer. So which one would I double if I was going to double one of them? I would probably want to, since the v goes all the way to 2 pi, it goes twice as much, so I probably want to take more steps for that. Not that it matters, but you know, now it kind of looks like that Earth longitude and latitude business. Looks a little bit more even. And remember, if you cut this down to something really small, like if I cut my phi down to just 2 steps, what do you think it's going to look like? Weird. That in itself is a shape parameterized by some other thing, but that's not what we want here. Oops. Okay. So we have good parameterizations for spheres and paraboloids, or things that have to do with spherical coordinates and cylindrical coordinates. The next thing to do is I kind of didn't do this with the earlier example, but if I'm taking a look at these as my parameter, phi and theta, they're drawing out this thing is drawing out a sphere, right? But let's take a look at where it actually comes from. Where it actually comes from is a phi and theta axis. Maybe I should have drawn this a little bit more proportioned. Where phi goes from 0 to pi and theta goes from 0 to 2 pi. Now we've kind of seen a map like this before, and I think I even talked about a little rectangular region here that would match up with a little patch over here. I think I talked about something like that before. And what happens to this patch is that, let's blow this up. Oh, jumps like that. And I think one of the things that we might have talked about was a tangent vector from here as being like a d phi length. I guess I should really call it delta, but I'm kind of jumping around. And being translated to I think the phis go this way. So being translated to another vector on the surface, and then a d theta vector over here being translated to another vector over here. And I think last time when we talked about this, we talked about the area being spanned by that parallelogram of those two vectors coming from this thing as some sort of area approximation of a little bit of a sphere here thing. I don't know if that makes sense. Yeah, and then we would add up a whole bunch of these patches to get our surface area. So that's what we're going to move towards. We're going to, I guess I needed to have talked about that today, but we're out of time. So the surface area is one of the first things we're going to look for here, and then we're going to carry that idea of a surface area to a function over a surface area, which is going to be kind of strange to think about. But we're extending and creating a new integral for what we're going to be working on. Okay, I have a couple of announcements. One, I made the labs due Wednesday before class, but there was a couple of labs that should have been due last week that I forgot to add on last week, so now you kind of have 4 labs to do by Wednesday. So good luck with that. 2, I don't know if you guys know that the makeup exams are up and available already. Did I announce that? I think I might have mentioned it, but here I have a chance to actually show it to you. On the top of your web access page, there are makeup exams, and then you just download the exams and do it. And then I think the makeup exams are exactly or almost exactly like your original exam, except they have this makeup on it. And then at the very last page, there's a little write-up, little short question and answer thing. Oh my, it's due on Thursday this week. Well, it's been up for a while, so. Well, too bad. So the idea is that you guys have whatever score that you got on the actual test. That's how much you've done already. So you can just do that and copy what you did if you got 100% on a particular problem. So all you have to really focus on are the problems that you didn't get. And by the way, this is an open note, open book test, so you can always research your book, your assignments, the internet, your classmates. You can research your classmates to get help. And any instructors or tutors, you can get help from them to see, if you can answer these things correctly. So the second makeup exam, I decided to throw an extra problem in there. I should have threw an extra problem for the first one too, but the second one has an extra problem, and you have to do that also. It's a multiple choice. That's not exactly the same as a multiple choice from the practice test, but it looks very similar. You just have to read it carefully. All right? Okay, that's it for today. I have more stuff, but I'll tell you guys next time.